Welcome to Lecture 9. In this lecture, we're going to start talking about the concept of eigenvectors and eigenvalues. And in this lecture, we'll simply introduce the idea, explain what these quantities are, and show how to find eigenvectors and eigenvalues for a 2x2 matrix. And then in the next lecture, we'll look at a higher dimensional case. So let's start with the definition of eigenvectors and eigenvalues. We can say that the non-zero vector v and, well, let's see, maybe I need to rephrase this. The non-zero vector v, is said to be an eigenvector of A with associated eigenvalue lambda if AV equals lambda V. And let me just stress again, lambda may have the value of 0, but V cannot be 0. And one way to think about this is that if we permitted ourselves to think of that possibility V is equal to 0, well, that would be an eigenvector for every matrix, because it doesn't matter what the matrix A is. If you multiply it by the 0 vector on the left-hand side here in this equation, you will certainly get the 0 vector on the right-hand side. So if we permitted 0 to be a possibility for an eigenvector, it would be an eigenvector of every matrix, and that's not very meaningful. So we do not consider the possibility that the eigenvector itself is equal to 0. However, in some cases, we will find that eigenvalue, this lambda, can be equal to 0. In other words, and this is the interesting thing, there are some cases where you can have a non-zero matrix A multiplied by a non-zero vector V, and yet you will still get 0 on the right-hand side. Even though the matrix and the vector are both non-zero, you can still get 0 over on the right-hand side here. And when that happens, then we know that one of the eigenvalues of that matrix is 0. And in fact, we will then usually want to find out what the associated eigenvector is, and we'll learn how to do that in just a moment. Now let's, just to make sure that this concept is clear, let's look at an example or two. 1, 1 is an eigenvector of the matrix 3, -1, 1, 1. The associated eigenvalue is 2. Now let's see why this is true. Well, if we take this matrix 3, -1, 1, 1, and we multiply it by the vector 1, 1, what do we get? Well, 3 times 1 is 3. Minus 1 times 1 is minus 1. 3 minus 1 is 2. And 1 times 1 is 1, plus 1 times 1 is another 1, and 1 plus 1 is 2. But note that this vector 2, 2 can be written as 2 times 1, 1. So that means that here we think of the matrix 3, negative 1, 1, 1 as being equal to A. The vector 1, 1 is playing the role well, there we go. The vector 1, 1 is playing the role of V, and then over here on the extreme right of the equation we have 2 times V. And so this is how we see that 2 is indeed the eigenvalue associated with the eigenvector 1, 1. So this is what we mean by eigenvector and eigenvalue. And now the question that probably occurs to you is this: how do we find the eigenvectors and eigenvalues of a matrix? And the answer to the procedure follows from the definition. So remember, we said that for V to be an eigenvector with associated eigenvalue of lambda of the matrix A means that AV is equal to lambda V. Now that can also be written as lambda times I times V, where I is the identity matrix. Remember, the identity matrix is the matrix that has 1 for all of the diagonal terms and 0 everywhere else. So we now have AV is equal to lambda IV. AV is equal to lambda IV. And now, if we take all of that to one side of the equation, we get AV minus lambda IV is equal to the 0 vector. And then this can be written like this: A minus lambda IV is equal to 0. Now remember, we're only considering non-zero vectors here for V. And so this equation tells us that A minus lambda I is a matrix such that we can multiply that matrix by a non-zero vector and obtain the 0 vector. Well, the only way that can be true is if the determinant of A minus lambda I is equal to 0. So we say this implies that the determinant of A minus lambda I equals 0. So, and from this equation, we can find the eigenvalues of A. Then, once we have found the eigenvalues, we can find the eigenvectors, or let's say the eigenvector associated with each eigenvalue. So let's see how this goes. Let's maybe, as long as we've looked at this matrix 3, -1, 1, 1, let's go ahead and look at it in a little more detail. So we'll say example. Suppose A is equal to the matrix 3, -1, 1, 1. And we want to find all the eigenvalues and eigenvectors. Okay? So we take A minus lambda I, we take the determinant of that and set it equal to 0. So we'll say determinant of A minus lambda I is equal to 0. Now, this gives us 3 minus lambda. Remember that I, actually maybe I should show that intermediate step. So determinant of 3, -1, 1, 1. You won't need to do this intermediate step every time, but maybe this first time it's worthwhile. Minus lambda times I, which is 1, 0, 0, 1. We want to set the determinant of that matrix equal to 0. Okay, so when we multiply lambda times the identity matrix, we get lambda 0, 0, lambda. And now we set that equal to 0. So that tells us that 3, when we do the subtraction of the two matrices, we get 3 minus lambda, -1, 1, 1 minus lambda, and that's equal to 0. And remember that to find the determinant of a 2 by 2 matrix, we just multiply the diagonal terms by each other and then subtract what we get when we multiply the off diagonal terms. So we will get 3 minus lambda times 1 minus lambda minus 1 times -1 is equal to 0. And when we multiply this all out, we get lambda squared and minus 4 lambda plus 3 plus 1 is equal to 0. And therefore, lambda squared minus 4 lambda plus 4 is equal to 0. Now this polynomial on the left-hand side of this equation is called the characteristic polynomial of the matrix. The equation is called the characteristic equation. For the matrix A. And notice that the degree of the characteristic equation in this case is 2, because A was a 2 by 2 matrix. If the dimension of A were 3, then the degree of the characteristic equation would be 3. If the degree of the matrix is n, if it's an n by n matrix, then the degree of the polynomial will be n. So the number of, and of course, the degree of the polynomial, or the degree of this characteristic equation, is going to determine how many solutions it has, or how many eigenvalues. So a matrix, an n by n matrix, will always have n eigenvalues. Now some of them may be repeated, so it may not have n distinct eigenvalues, but it will have n eigenvalues. Okay, and let's see in this case, if you try to solve this equation, you will notice that this can be factored as lambda minus 2 quantity squared is equal to 0. So in fact here we have what's called a repeated eigenvalue. The eigenvalue 2 is repeated 2 times. And of course we already knew that 2 was an eigenvalue for this matrix. We found that up here in our first example, but now we see that it is the only eigenvalue for the matrix. There are no other values that the eigenvalue can have for this particular matrix. The only possible value for the eigenvalue is 2. And now let's suppose that we didn't know that 1, 1 was the corresponding eigenvector. How could we find that out? And also, how can we find out if there are any other eigenvectors associated with this eigenvalue? So let's say this shows how to obtain the eigenvalues. Now, how do we obtain the eigenvectors? Well, once again, we go back to the defining equation. A v is equal to lambda v. Now, the way I'm going to show you here is a little bit different from what's in the book. Either way is correct, and you just choose whichever way you like. But we'll say, okay, A then is 3, negative 1, 1, 1. And for the vector v, we'll have x, y. Now, lambda, we've just found out, is equal to 2. And again, v is equal to x, y. Now, if we conduct the matrix multiplication on the left-hand side, we have 3x minus y as the first component and x plus y as the second component. And on the right-hand side, we get 2x, 2y. So now, if we look at these two vectors, which are supposed to be equal to each other, we get 3x minus y is equal to 2x, and x plus y is equal to 2y. Well, notice that both of these equations imply that y is equal to x. Now, that doesn't give us an exact value for the eigenvector, but it tells us something about the eigenvector. In other words, the eigenvector will be the set of all vectors, all non-zero vectors in R2 such that y is equal to x. We can pick any one of them, and all the others will be a multiple of that one that we pick. And so perhaps we'll pick v is equal to 1, 1, just like the example that we had above. And we already know that that works, but let me note that 2, 2 would also work, and let's just see that that's true. So if we took 3, negative 1, 1, 1, and multiplied it by the vector 2, 2, let's see what would happen. Well, 3 times 2 is 6, minus 2 is 4, 1 times 2 is 2, plus 2 is 4, and sure enough, that is equal to 2 times 2, 2. So again, a matrix, here we have a matrix times a vector is equal to 2 times that vector. So the eigenvector is not unique. It's unique only up to a scalar multiple. But this is the eigenvector. 1, 1 is the eigenvector that we get. And notice that there are no other eigenvectors that we get that are not multiples of this. All the eigenvectors of the matrix A will be multiples of this one vector, 1, 1. And so, therefore, this matrix is said to not have a complete set of eigenvectors. Now, what do we mean by that? A matrix is said to have a complete set of eigenvectors if the number of linearly independent eigenvectors is equal to the degree of the matrix. In other words, if it's let's say a 5 by 5 matrix, and if it has a complete set of eigenvectors, then that means it has 5 linearly independent eigenvectors. And sometimes when you have a repeated eigenvalue, you can still have a complete set of eigenvectors. In fact, we can say the only time, though, that you can have an incomplete set of eigenvectors, like we have here, is when you have a repeated eigenvalue. But that doesn't necessarily mean that it's incomplete. In fact, let's see that. So let's complete this example. Let's say all possible eigenvectors of A are multiples of the vector 1, 1. So A has only one linearly independent eigenvector. In other words, A does not have a complete set of eigenvectors. This can happen only when A has a repeated eigenvalue. However, a repeated eigenvalue, the existence of a repeated eigenvalue does not necessarily imply that the matrix will not have a complete set of eigenvectors. And as an example of that statement, let's look at this. Let's say find all eigenvalues and eigenvectors of A equals 2, 0, 0, 2. Okay, so here's another 2 by 2 matrix, and we want to find all of its eigenvalues and eigenvectors. Well, we know now when we set the determinant of a minus lambda I equal to 0, we're going to get this equation, and this can be written as 2 minus lambda times 2 minus lambda minus 0 times 0 is equal to 0, and therefore 2 minus lambda squared equals 0, and therefore lambda, we again have a repeated eigenvalue of 2, just like we did with the previous matrix. It had a repeated eigenvalue of 2, as we saw right here, and so does this completely different matrix. It has a repeated eigenvalue of 2. Now, for the previous matrix, we saw that it did not have a complete set of eigenvectors. It only had one linearly independent eigenvector. Let's see about this one. So let's say now find the eigenvectors of this matrix. Okay. And now remember, to find, once you have the eigenvalue, to find the eigenvector, what you do is you go back to the defining equation. AV is equal to lambda V. So we have 2, 0, 0, 2 times x, y is equal to 2 times x, y. And when we multiply out both the left hand and right hand side, we get 2x, 2y is equal to 2x, 2y. And so x is equal to x, and y is equal to y. Now that's certainly not news. That's always true, that x is equal to x and y is equal to y. So what do we conclude? We conclude that any non-zero vector is an eigenvector of this matrix. So it is simple to find two linearly independent eigenvectors. And most people would choose something like this: 1, 0, and 0, 1. That's the simplest choice that you can find. These are obviously linearly independent vectors, and each of them is an eigenvector of the matrix 2, 0, 0, 2. Now, you could not find 3 linearly independent eigenvectors because, after all, these are vectors in R2. So you can only find 2 linearly independent eigenvectors in R2. And so since the number of linearly independent eigenvectors is equal to the degree of the matrix, then, or the order of the matrix, then this matrix, so this matrix does have a complete set of eigenvectors. Now let's look at one more problem, and then we'll or one more example, and then we'll look at some problems for this section. So let's look perhaps at problem 4. This is 8.1.4. And the matrix in this case is A is equal to 1, 2, 2, 4. I strongly encourage you to stop the video at this point and try to find all the eigenvalues and eigenvectors yourself, and then come back and let's compare. Okay, so I hope that you had luck with this problem, and let's see how it would go. When we set the determinant of a minus lambda I equal to 0, we get 1 minus lambda, 2, 2, 4 minus lambda is equal to 0. So we get 1 minus lambda times 4 minus lambda minus 2 times 2 is equal to 0. And so this says lambda squared minus 5 lambda plus 4 minus 4 is equal to 0. And therefore lambda squared minus 5 lambda is equal to 0. And fortunately, this is a case where we don't have to go to the quadratic formula, because we can factor this as lambda times lambda minus 5 is equal to 0. And therefore, we have the two eigenvalues, 0 and 5. Now, anytime that all the eigenvalues are different, like this case, anytime that's the case, then the matrix will definitely have a full set of eigenvectors. Each one of the distinct eigenvalues will have an associated eigenvector. So this is, you might regard this as sort of the easy case. So we can, what some people will do is they'll number the eigenvalues, they maybe call lambda 1 the 0 eigenvalue, and lambda 2 is equal to 5. And now we want to find V1 and V2, where V1 is the eigenvector associated with lambda 1 and V2 is the eigenvector associated with lambda 2. So let's see how this would go. Again, in both cases, what we do in order to find the eigenvector is we start back with the defining equation. So A times V1 is equal to lambda 1 V1. And so we have A, let's remember, A is 1, 2, 2, 4. So 1, 2, 2, 4, x, y is equal to lambda 1, which is 0, x, y. And now when we multiply both the left side and the right side, we get x plus 2y, 2x plus 4y. And on the right, we will get 0, 0. And so x plus 2y is 0, and 2x plus 4y equals 0. And notice that both of these equations, if you do just a little bit of algebra, you will come up with a conclusion that both of them imply that x is equal to negative 2y. Now, any vector in R2, any non-zero vector in R2 that satisfies that equation will be an eigenvector of A with associated eigenvalue of 0. So let's just pick something easy. We'll pick negative 2, 1. Because certainly for the vector negative 2, 1, and that's V1, for that vector, it is true that x is equal to negative 2 times y. And if you wish to check, okay, we have 1, 2, 2, 4 times negative 2, 1 is equal to 1 times negative 2 is negative 2, and 2 times 1 is positive 2, and negative 2 and 2 is 0. And then 2 times negative 2 is negative 4, 4 times 1 is positive 4, negative 4 and positive 4 is 0. And sure enough, that's equal to 0 times negative 2, 1. And this will be true for any multiple of the vector negative 2, 1. However, you cannot find any other eigenvector that is not a multiple, any other eigenvector associated with the eigenvalue 0 that is not a multiple of negative 2, 1. So this is the only eigenvector associated, or this can be considered to be the only eigenvector associated with the eigenvalue 0. So V1 is negative 2, 1. Now let's try to find V2. Okay, here the defining equation is A V2 is equal to lambda 2 V2. And so this gives us 1, 2, 2, 4 x, y is equal to 5, because lambda 2 is 5, remember? 5 times x, y. And so x plus 2y, 2x plus 4y is what we get on the left-hand side, and on the right-hand side we get 5x, 5y. And now when we equate these, we get x plus 2y is equal to 5x, and 2x plus 4y is equal to 5y. And the first equation, when we substitute, we subtract x from both sides and then divide by 2, we get y equals 2x. And for the second equation, if we subtract 4y from both sides, we get exactly the same, y equals 2x. So any non-zero vector that satisfies that, any non-zero vector in R2 that satisfies that equation will be an eigenvector of the matrix with associated eigenvalue of 5. And again, we'll keep it easy. We'll pick V2 is equal to 1, 2. Because surely for that vector, y is equal to 2x. And again, if you wish, we can check this. 1, 2, 2, 4 multiplied by the vector 1, 2. Okay, we have 1 times 1 is 1, plus 2 times 2 is 4, 1 and 4 is 5. 2 times 1 is 2, plus 4 times 2 is 8, 2 and 8 is 10. And that is equal to the same as 5 times 1, 2. So we have the matrix times the vector is equal to 5 times the vector. So this shows you that indeed 1, 2 is an eigenvector with associated eigenvalue of 5. And here we could check up for that one too. So here V2 is equal to 1, 2. And that is it. That's how these problems go in the simple case of finding the eigenvalues and eigenvectors of a 2 by 2 matrix. So now we'll look at some problems related to this, and then in the next lecture we'll go up to the 3 by 3 case and maybe higher. Okay, so for the problems for this lecture, let's try the following. Problem 9.1 will be problem 8.1.3 in your textbook, and problem 9.2 will be problem 8.1.9 in your textbook. So those problems will conclude lecture 9, and good luck.